questions for me, like homework questions for me? Mackenzie. 4.3 number 16. Yeah, like a dum-dum, I didn't have the PDF open yet. So it'll just take me just a quick second to pull that up. Come on. You said 16? Yeah. 1, 6? Okay. So this question asks you to do several things. It wants you to find the intervals in which it's increasing and decreasing, then any local maxes or mins, and then to do the intervals of concavity and the inflection points. So you have several things to do here. First thing I'd want to do is just make note of the domain of this function, since I'll need that for the critical values later on to decide if the things that are undefined in the derivative are actually critical values or not. So what's the domain for this going to be? Nope. The problem is the log in there. Yeah, x has to be greater than 0. So you can't do log of 0, can't do log of a negative. So that's that. So if we take the derivative, this is going to be a product rule situation. So derivative of, the first times the second plus the first times derivative of the second. So this just becomes 2x log x plus x. Everybody okay there? Worth noting here, before we reduced, we should really inspect that to see if there's values where f of x, or f prime of x doesn't exist that are inside the domain of f. So again, the places where we'd have to be careful is here, right, where x can't be 0, but 0 wasn't in the domain of f anyway, so we're all good to go. We still got a natural log in there, so that's fine. Whatever the natural log was undefined in f, it'll still be undefined in f prime, which is fine. All right, so searching for critical values is only going to matter when the derivative is equal to 0. So that's that. To solve that, I'm going to solve by factoring. So I can take out a greatest common factor of x. Oops. And then apply the zero product property and set each of those factors equal to 0 and solve. So x equals 0, and then we have the natural log of x is going to equal -1/2. So to get that x by itself, we'll do exponent base e to the both sides. So x is going to equal e to the -1/2. All right. So let's go ahead and make a little diagram here. E to the -1/2 is a positive number, so I know that's to the right of 0. Everybody's cool with that? Okay. And over here, I know I don't have anything. Why do I know that? Yeah, the domain is greater than 0, right? So this guy even doesn't matter, right? So that's actually not a critical value because it's not in the domain. Just FYI. I'm going to still use it as a landmark to pick on the other side of, but not technically a critical value. 0, because it's not in the domain of f or f prime even. So let's pick a number between 0 and e to the negative 1/2. About e to the negative 1. Everybody agree that's smaller than e to the negative 1/2? Since it's 1 over a bigger number, that makes it smaller. I like that because I can plug into the natural log and it'll be easy to see what I got here. I could conceivably, again, not that this would be a no calculator problem on the AP exam, but like when possible, I'm going to treat every problem as a no calculator problem and just kind of show you how to do it without a calculator. Is everybody okay with how I plug that in? The natural log of e to the negative 1. The natural log cancels out the e and you're just left with the negative 1. And then probably e to the first makes sense to do over here, right? Or even 1 would be okay. Let's do that. That's probably even easier, right? So 2 times 1 times 0 plus 1 is 1. So e to the negative 1/2 goes from decreasing to increasing. That's a local min. And we're decreasing then from 0 to e to the negative 1. And we're increasing from e to the negative 1 all the way out to positive infinity. So let's see, that's part A, that's part B. Mackenzie, still doing okay? Okay, to do part C, I need the second derivative. Oh, yeah, thank you. Yep. Just typoed. Oops-a-daisy. Great catch. I love the eye for detail. Natural mathematician there. All right. So second derivative, the derivative of 2x log x is another product rule. So derivative of the first plus the first times derivative of the second. And then I still have the derivative of the x at the end. So there's that. Again, I note that the domain for this is the same as the domain for f, so we're good to go there. So we have simplify down to 2ln x plus 3. So I'll set that equal to 0. So here I get e to the negative 2/3. I sped through that. Is that okay with everybody? Just skip anything algebra there. Oh, sorry, 3/2. Good thing I went back and checked. You guys shouldn't have been okay with it. Should have been like, no, Mr. Kulik, your algebra stinks this morning. Yeah, I know. So I'm going to put the 0 there because I know that nothing happens before that. Just so I don't get tempted to pick a negative number there or something, right? Yeah. I did it again. Glad you guys are paying attention this morning. You're on one. Oops. Wrong sides, though. All right, 1 over e squared is going to be smaller than 1 over e to the 1.5. If I plug that in, I get 2 times negative 2 plus 3, so that's negative. And if I plug e to the negative 1 in, I get 2 times negative 1 plus 3, that's positive. So this guy is an inflection point, and we are concave down from 0 to e to the negative 3 over 2, and we're concave up from e to the negative 3 over 2 to positive infinity. That one was a workout, Mackenzie. A lot of stuff to do on that one. I guess that makes it a good choice then, right? Does that feel okay to you, though? What we did? Again, lots of easy places to make mistakes. There's a lot of like Algebra 2 stuff that maybe doesn't come back super quick. Mia. Sure. All right. So the directions for this are just to sketch the graph that has the following attributes. So I would start, when I look at this, I hate that. I'd want to start by just rewriting that in a way that I'm not going to be confused by it. So the absolute value of x is less than 1, means that x needs to be between negative 1 and positive 1, right? If I do negative 0.9, that would be okay. If I do positive 0.9, that would be okay. If I do something smaller than negative 1 or bigger than positive 1, it would not be okay. Now, if I want things between, x has to be between 1 and, or absolute value of x needs to be between 1 and 2. So that means that like x has to be between 1 and 2, or x has to be between negative 1 and negative 2. And then x greater than 2 would mean x would have to be less than negative 2 or greater than positive 2. So I'm just going to start by just kind of like decoding those absolute value inequalities, which are just kind of an annoying way to write it. I understand why they did, because it's like compactor. But for me, trying to draw a picture, I kind of hate it. You know what I mean, guys? And just like, that's one more thing to think about. All right, so the x values that I'm going to care about are going to be 1, negative 1, 2, negative 2, So I'm going to go ahead and put those on there. We have some x-intercepts here that are given, so let's just start by kind of drawing those in. Everybody's okay there? And now let's start, I'm going to do some color coding here. So I'm going to erase all my highlights. So I'm going to do, this section is going to be my decreasing section. So I'm just going to highlight that for myself. Between -1 and +1, we should be decreasing. Oh my goodness. Guys, I drew those in there. Those are not the green, that wasn't x-intercepts. Those were, yeah, those were extrema. Ay, ay, ay. Well, I'm not going to draw those in yet. Okay, so this is decreasing. I was like, how am I going to draw decreasing from one with no, and it's like, hey, there's got to be an answer. I'm like, oh, I just read this wrong. I'm super dumb. Okay. And then it says that here, f prime is equal to exactly -1 here, where we're less than 2. So what does a slope of -1 look like? It's a diagonal line, straight line, pointing down, right? So like, and then, oh, that's to 2, sorry. So, I don't know, I'm going to put it there. And then I'll do the same thing down here. I'll put it like right there. Then give me any other specific information about those coordinates. So I'm just going to just kind of stick it in there where I want it. Yes. Because it's a greater than. So like -3 would satisfy that, and +3 would satisfy that. So it's like, instead of having an and inequality where you're between two things, you have an or inequality where it's like either side of two different things. You know what I mean? And then let's see, this section here is my increasing section. So I'll do that to just kind of remind myself that I'm increasing there. And then the last piece that I have is that I am concave down from here to here, and I have an inflection point at 1, 0, or 0, 1, excuse me. So there's my inflection point. So what does that tell me then? Is that we're going to be concave down after that, right? Or I'm sorry, concave up, 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 up. Okay. So I'm going to turn around and I'm going to be increasing, but I need to be concave down. So it's going to look like that to my maximum. Then I'll keep on concave downing. And then we'll switch to concave up. And at negative or positive 1, I'll hit minimum, and then we'll finish. So look something kind of like that. I think hits all my criteria. And again, it's just a sketch, so like your answers will vary. Like your picture could look a little bit different than mine, but like should still be basically the same shape. Does that feel okay? So I think taking some time to just like remind yourself what's going on where helps me tremendously when I'm trying to draw this thing. Even if it's just like writing like, like increasing, right? Or whatever if you don't have highlighters, but because it's hard to kind of hold all that stuff in your head at one time. All right. Probably have time for one more. Anybody got one more? If you don't, that's okay. We have time next time and the time after and the time after. Mia? Yeah. Yeah. All right, let's see. 58, you said? And we are just looking for the absolute mins and maxes on the given interval. Okay. All right. Bless you. You're welcome. Okay, so we'll start by doing the derivative. Well, let's do this also along the way. What value is cotangent undefined at? Because we know that there's cotangent can be undefined somewhere, right? Cotangent is the same as cosine over sine, right? Sine is 0 at pi over 2 and 3 pi over 2. Now, inside of here, I need really, since I have t over 2, I would need to have pi inside of here, which I do, and I would need to have 6 pi in there. Nope. 3 pi would need to be in there, which I don't. So there is one place where I have, where the function is undefined. I'm just going to kind of keep note of that. All right. So I'm going to go ahead and do my derivative. So the derivative of t is just 1. And the derivative of cotangent t over 2 is a chain rule problem, correct? The derivative of the outside is negative cosecant squared of the inside times the derivative of the inside. So far, so good? Okay. Now I need to look at where cosecant squared is going to be undefined. What's the great news? Well, it is, but it's at the same place that cotangent is going to be undefined, because cosecant is 1 over sine. cotangent is cosine over sine, so they're going to be undefined at the same place, which is wonderful news for me. So right away I can write down pi as one of my values I have to check. You good with that? Now, anyways, we'll get to it. And now we'll just set this equal to 0. Oh, do I really have to check this? Is f defined at pi? No. So do I need to worry about that as a critical value? No, I do not. So we don't need to worry about it because well, it's not in the domain of f, right? It's inside of the interval that we want to find our maximum minimum on, but it's not defined there. Anyways. Okay, so I'm going to subtract 1 and then multiply both sides by -2. Oops. So I get that. And then I'm going to just do the reciprocal of both sides, because I'd rather deal with sines rather than cosecants. Okay with that? So we'll square root both sides. If I rationalize that denominator, square root of 1/2 is square root 2 over 2. Where is sine equal to plus or minus the square root of 2? Well, that happens at pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, etc., right? You good with that? Okay. Now I'm going to multiply both sides by 2 to get the t by itself. I don't know why I put a 2 there. It's because I was getting a step ahead of myself. But remember, we're only worried about the intervals from pi over, or the interval pi over 4 to 7 pi over 4. So all that stuff is gone. So we need to check then f of pi over 2, f of 3 pi over 2, and what other values? We also have to check the endpoints of our interval. And so now I would say it's calculator time. Although I guess I could probably do these in my head if I had to, but like, can we not? What do you guys say? Okay. So now all I'm going to do is I'm going to go back to f, and I'm just going to type this in, and we're just going to use the y equals notation. To do cotangent of t over 2, I'm going to do tangent x over 2, and then I'm going to raise that to the -1 power. Notice that's not the same as tan inverse. That's the reciprocal of tangent. I got to make sure we're in radian mode. Okay, good. So that's just going to be y1 of pi over 2. There's that. 3 pi over 2. Okay. Pi over 4. I'm going to do 7 pi over 4 first because it's going to be less keystrokes. So that's that. Okay, so this can't be anything, right? 3.08, because it's not the smallest thing, not the biggest thing we found so far. And then we got to do pi over 4. Also can't be anything. So my local, or my minimum was at pi over 2, and that minimum is 257. And my maximum is at 3 pi over 2, and it's 371. And these are globals because we're only operating inside this single interval. Yeah, global and absolute are the same. They're interchangeable. What was this? This is like 308. This is like 319 or something. I'll write those down anyways. So those guys are just regular old maxes or local maxes and mins, but we don't care about which one is which. Does that feel okay? So the trig was kind of rough there at points, but all right. Today we're going to talk about section 4.7, which is about optimization problems. These are similar in a lot of ways to like the related rate problems. I know. All right. So our first step is to understand the problem. You got to read the problem carefully, and you got to keep reading it and thinking until you really understand what's being asked or what's going on. Questions you might want to be thinking about while you're doing that is, what are the unknowns? What are the given quantities? What are the given conditions? The second step would be to draw a diagram. In most of these problems, it's going to be extremely useful to have a picture to rely on, especially one that you can label the quantities on. A lot of these are going to be geometric in nature. So like, like you have a cone and a cylinder's inscribed in it. Like, what's the biggest possible cylinder you could fit in there, or the cylinder with the greatest volume or surface area, whatever, something like that. Step 3 would be to introduce notation. So you want to assign a symbol to the quantity that's being maximized or minimized. They're going to use the capital Q for now. And then select symbols like A, B, C, D, etc. for other unknown quantities and label the diagram with these symbols. And it says, as the no dur of the century, consider using like suggestive symbols like capital A for area or lowercase h for height. Would never thought of doing that. Yeah, right. Step 4 would be to express Q in terms of some of the other symbols from step 3. If Q has been expressed as a function of more than one variable in step 4, use the given information to find relationships in the form of other equations among these variables. Then use these equations to eliminate all but one of the variables in the expression for Q. Q will be expressed as a function of one variable, say x, so you'd have Q equals f of x, and then write the domain of this function. So just like we did in a lot of these related rate problems where we had to eliminate, like the radius or the height or something in some of these cone problems, we made similar triangles. You guys remember doing that? Same sort of tricks we'll use here. And then step 6 would be use the methods of section 4.1 and 4.3 to find the absolute maximum or minimum value of f. In particular, if the domain of f is a closed interval, then the closed interval method in section 4.1 can be used, i.e. you also have to check the endpoints in addition to any critical values. All right, that's the gist of it. The rest of the day is just going to be doing examples of this process. So there's no extreme new content. It's just going to be all application, so there's nothing new theoretically happening. We're just going to kind of get used to some new types of problems and how to deal with these. All right, so a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fencing along the river. What are the dimensions of the field that has the largest area? Does everybody understand kind of what's going on? So I'm going to next then start by drawing a picture. So there's my river. There's my fence. Everybody's cool with that? Let's introduce some notation here. What am I trying to maximize here? Area of the field. So I'll write a little note to myself that I want to maximize the area. What shape is this field? Rectangle. So what's the formula for the area of a rectangle? This is something I would expect that you memorized. Length times width. So let's label then our drawing. So I'm going to label widths and lengths on there. Everybody feel good about that? So we've written an equation for the quantity that we're trying to maximize in this case. What's wrong with the equation we've written though? Two variables. So I need to find a way to eliminate one of them. What am I going to use to do that? What can I say about the 2,400? All of my fencing has to equal 2,400, correct? Everybody agree with that? Or rather that L is going to equal 2,400 minus W. So if I want to write an equation for area in terms of W, oh, thank you. I can say that. Okay. What is the domain for this function going to be now? What values of w can I feasibly plug into this? Remember, w represents the width in this picture. Has to be greater than 0. Everybody agree with that? And it also has to be less than what? Not 2,400. I mean, it certainly does have to be less than that, but that's not the... Look here. $1,200, because anything bigger than that is going to create a negative area, correct? Everybody's cool? Okay, let's do some calculus now. So I'm going to start by just simplifying my expression so that I don't have to do a product rule when I do my calculus. Believe it or not, we've done the hard part, guys. So I've done that. I'm going to set this equal to 0. Since it's a polynomial, I know that there's no places where the function can be undefined, so I don't have to worry about any of those critical values. I'll subtract the 2,400 over and then divide by 4. So I have to worry about when w is 600, 0, and 1,200. And I'm just going to check those to see which one gives me the biggest value. Well, a of 0, that's easy to see, that's 0. A of 600 gives me, what is that going to be? 1,800 times 600. 6 times 18 is 72? No. 90, what did I say? 6 times 600, 6 times 18 is, whoa, Boise. Yeah, it's 72. And then a of 1,200, again, we can see is 0. Okay. Does everybody feel okay so far? So one of my dimensions is 600. How am I going to find the length then? And just plug it back in up there, right? And I should probably have a unit on here. I forget if this was feet or were these were feet. So that's my length. And this was my width. Is that okay with you guys? What was the trickiest piece? was getting to here, right? After we had our equation and the domain for it figured out, the calculus piece was pretty straightforward, right? That'll be common for these types of problems. The hardest part is going to be getting it set up correctly. The calculus should be pretty easy after that. All right, next up. So a cylindrical can is to be made to hold 1 liter of oil. Find the dimensions that will minimize the cost of the metal to manufacture the can. Okay, we want to minimize the cost of the metal to manufacture the can. What are we really asking about there? Surface area. Excellent. So we want to minimize surface area. Okay. So let's draw our picture real quick, I suppose. So we're just going to have just like a regular old cylindrical drum. How do I calculate the surface area for a cylinder like this? Yeah, 2 pi r squared, one for the area for the top, one for the area of the bottom, and then plus 2 pi r h, which is for the rectangle that's the sides, basically. Right, if we unwrap the sides, it just turns into one big rectangle. Okay. Everybody happy with what we have here? What's the problem with the surface area equation that we've written? 2 variables, r and h. What are we going to use to get rid of one of them? Math. Great insight. We're going to use this. The can needs to hold 1 liter of oil. What is it describing there? What measurement is it describing? The volume. So the volume of my cylinder, 2 pi r squared h, needs to equal 1 liter, which is the same thing as 1,000 centimeters cubed. Chemists among us might remember that conversion. 1 milliliter is 1 cubic centimeter. If you think about it, like a cubic centimeter is just like a little tiny square. That's like about a milliliter. So I'm going to use that then to get the H by itself. So I can substitute that in for surface area. Is everybody okay with what I did there? So I'm going to go ahead and do some simplifying so that before I do my calculus, I can make my life a little bit easier. Everybody cool with the way I wrote that? And boy, that looks a heck of a lot easier to differentiate than what it was written before, right? Do yourself a favor, Simplify before you try to take any derivatives. So I'll set this equal to 0. Oh, what do we forget to do, guys? Yeah, what's my domain here gonna be? Well, what if h is less than 1? I'll agree with that, and I'm going to put it strictly greater than 0 because notice there's an r in the denominator. If r is actually 0, this whole thing is undefined, right? So we'll make it strictly greater than 0. Is there have to be an upper bound to this, though? I don't think there does. I think this will be okay to be unbounded. If you think about it, like r can keep getting bigger and bigger and bigger, h is just going to get infinitely tiny short, and you'll still get a cylinder that can hold, 1,000 cubic centimeters, right? So I think we're okay with just that, which is lovely, because what does that make the next process way easier, because there's less stuff to check. All right, now we'll set this equal to 0. Oh, well, let's do this first. We'll note that this is undefined when r equals 0, right? Does that matter, though? Mia is shaking her head. No, why not, Mia? Yeah, because 0 is not in the domain of the function. So it doesn't matter that it's not in the domain of the derivative. So that doesn't matter to us. Write that as a subtraction problem here. Okay. What do you want to do first to solve for r? Oh, guys, let's do this. Why is that going to be nice? Yeah, it gets rid of the negative exponent. And in addition, I'm going to end up with an r in only one place. Boy, that makes life a heck of a lot easier to deal with, right? No fraction, no negative exponent, r in one place. Woo! Mr. Kulik. Now we're cooking with some gas here. All right, I'm going to add the 2,000 over, divide by the 4 pi. I'll note that I can reduce this a little bit. And then we'll do the cube root of both sides. Note, for odd roots, there's no plus or minus generated, which is nice. So the cube root of 1,000 is 10. I guess these are centimeters. So that's the radius. What did it ask for? Dimension. So we need the h as well. So now I'll just take my h from before. Let's just write it this way. This will make it easier. Everybody's okay with that? And I can simplify that up a bit. So that's going to make a reciprocal here, right? So I'm going to end up with 3 over 2 pi squared over 10 squared. So I can reduce those fractions. So like the 10 squared and the 1,000 become a 10. I have a pi to the negative 1 and a pi to the negative 2/3. So I'm going to be left with pi to the negative 1/3. And then I have a 2 to the negative 2/3. And I think that's probably okay for me. And since this is this was the only critical value, there's nothing really to check here, right? The answer comes tumbling out. Since I had an unbounded interval I was solving over, just r had to be greater than 0. And there's only one solution to the derivative set equal to 0. There's nothing to check here. This is my answer, I'm done. Is that okay with you guys? Would it be okay to give these as decimals? Yeah, for sure. For sure. You could give them as decimals. It's okay. You could just type in your calculator and spit out the decimal. That is okay. Again, Mr. Gould is going to treat these all as no calculator problems every chance he can, because you can type stuff into your calculator at this stage of the game. I'm quite confident, but I just like letting you guys see how would you go about doing this with no calculator. Elvis.
So what happens when the derivatives?
Oh, it's because that's where a maximum or minimum is going to occur, is where the derivative is 0. So all we're doing right now is finding the critical values and then checking the critical values to see which one is bigger or smaller. But since we're minimizing and there's only one critical value, it's clear that that's it. That's the minimum. All right. All right. I don't care about that. Let's just do another example. All right. Example says, find the point on the parabola y squared equals 2x that is closest to the point 1, 4. Well, it seems relatively straightforward in terms of what it's talking about. So let's plot our parabola here. So if I pick x to be 0, what does y have to be? 0. Okay. If I pick x to be 1, what does y have to be? Plus or minus the square root of 2, which is like 1.4-ish. If I pick x to be 2, what does y have to be? Plus or minus 2. And that's probably enough to get me a decent looking picture. Everybody's okay with that? Okay. So what we're going to be looking for is some point on this parabola such that the line to that point from 1, 4 is perpendicular to the tangent line. That's what we're looking at. Now, in other words, what's the other way we could think about this? If we're looking to find the point on the parabola that's closest to 1, 4, I guess let's give this a name, call it point P. What else could you consider it is that we're doing? We're minimizing the distance from 1, 4 to P. You guys buy that? I guess I'll call this guy something here. I don't know, just call him A. So we want to minimize AP. How to find the distance from A to P? Call that XY for the sake of argument. Anybody? X2 minus x1 squared plus y2 minus y1 squared, all square rooted. That's the distance formula, right? That's an expectation that I would have that you remember that. So in our case, let's make point A will be our x1, or our point A is going to be our x1, y1. And then our point for point P is going to be xy. What's our issue here? Two variables. Okay. How do we eliminate one of them? Let's do that. What else could have you done? You could have substituted square root of 2x in for y. How do you know that it was going to be positive 2x versus negative 2x? because you get a plus or minus. Well, look at the picture you drew. Right? Look at the picture we drew. Definitely should be in the positive, right? Should be in the first quadrant. You guys agree? Okay. Domain? So what values can the y-coordinate take on in this picture? All real numbers, right? The graph has arrows pointing down and pointing up. You'll cover all the y-coordinates. So the domain for our function here, since we wrote it in terms of y, is just all real numbers. Everybody's happy with that? Sophia?
Why is that?
Look at the picture. The y is the y-coordinate, right? What y-coordinates are possible in our picture?
Yeah.
All of them.
My brain was domain right now. I was like, why? Okay.
I know, because y is the input for our function. We have like a d of y. Yeah. That's okay. All right. So let's do the derivative then, right? Mr. Kulik's not going to do that. Not first. What do you suppose he's going to do first? Yeah, I'm going to square both sides. Now, is that okay to do? Right? The minimum of d is going to occur at the same place as the minimum of d squared. Surely, right? Everybody agree with that? Since the distance is always a positive quantity anyways, it's surely okay to do that. Now, why did Mr. Kulik want to do that? Yeah, great googly moogly makes the calculus a lot easier, doesn't it? All right. So if I do that, I get 2d equals 2y squared over 2 minus 1 to the first times the derivative of the inside, which is just going to be 2y over 2 plus, then 2y minus 4 to the first times the derivative of the inside, which just would be 1. Is everybody cool there? Okay. So solve equal to 0. Let's see, when I distribute that through, I get y cubed minus 2y plus 2y minus 8, or just y cubed minus 8. So y equals 2. Everybody's cool with that? What are the two other solutions? That's a third degree polynomial. Why aren't I worried about the other two solutions? They are imaginary. How do I know immediately that they're imaginary? Why didn't Mr. Kulik bother to go searching for any other solutions to this? How did he know immediately that the other two solutions were imaginary? That is a difference of two cubes. The other two solutions for a difference of two cubes always has two imaginary, one real. So two imaginary, one real. And the one real is always easy to get. All right. So this should be the minimum, right? How could we check to confirm it? If I take the second derivative, I should get something that is always positive. So let's do that real quick. So I'm going to get 3y squared, right? All I did was differentiate that. Not the thing that was terrible. It was really complicated. The thing that I foiled all the way, or I simplified all the way down that I solved. Is that something that's always positive? Yep. So that's where my minimum is occurring. So what is the value for x there? If y equals 2? X is going to equal y squared over 2. So 2. So we have the point 22. Everybody's cool? Sounds like I'm out of time here. That's okay. I just had a couple more examples that we would have looked at. The homework is there posted. We can do some more examples tomorrow if you guys still want. But take a look at this for next time.